now let us look at a case where I have two dissimilar particles, exactly similar approach. Okay. Instead of similar particle that you had, you have two dissimilar particles. That means I have a container where you have a particle 2 and particle 3 which are interacting via a medium 1 in exactly similar fashion. I can write what is the change in the potential energy or the change in the interaction energy. Okay. And again, if I assume that each term depends in a exactly similar way on the distance of separation and the dimension of the particles, then I could write A312 as A11 plus A23 minus A12 minus A13, right. And this A11, okay, I can write it as A11 per half multiplied by A11 per half, right. It is just a right. Now, A23 I can write it as A22 per half, A33 per half. This is actually from again the geometric mixing rule. Okay. Similarly, I can write A12 as A11 per half minus multiplied by A22 per half, and this is A11 per half multiplied by A33 per half. Okay. I can rearrange a few things. If I look this up, right. So, what is common here? I can take this term, okay, and this term. So, therefore, I can write it as A11 per half to the power A11 half minus A33 half, right. That is if I take these two terms, right. A11 per half is common, right. I have taken that. So, what is left here is A11 per half minus A33 per half. Now, here what I can do is plus I can do I can take minus, I can take let us do this way. What is common here is A22, I take plus A22 per half, right, multiply this plus here, right. So, A33 per half minus A22 per half, right. Is it okay with these two terms? Okay. Now, what I can do is what is that?
A1 power half minus A33 power half.
No, this is A11, sorry, this is A33, this is A11, right. Okay. And I can rearrange this. So, if I take if I have taken minus here, okay, then what I would have had is plus A11 per half minus A33 per half, right. So, therefore, A11 per half minus A33 per half multiplied by A11 per half minus A this is no this is oh okay, let me do it again. Let us do it again. Okay. So, if you look at these two terms, A11 per half, right, that is common. So, what I can do is I can write A11 half, I can take it out, right, and I have A11 half minus A22 half. Is that okay? That is with these two terms, yes. Okay. Plus I have A33 half, I have taken it as common. Now, I have A22 half minus A11 half, that is okay. Okay. Now, what I do is because I have one is positive, other one is negative here, right. So, what I can do is I can take like say A22 half minus A11 half common. Okay. I am going to take this as common, therefore, this becomes minus, I have minus A33 half, sorry, that becomes plus, right, that is correct, that becomes plus, okay, and I have minus, so minus A11, that is correct, it is minus A11 half, right. See,
it doesn't match with the
no, it matches, so it matches, I will tell you, it matches, right. So, what I do, so I take A22 half minus A11 half as common, right, multiplied by, because I have taken this as, okay, therefore, this becomes negative, right, minus A11 half, okay, negative, and I have plus A33 half, right, that is A33 half minus A11 half, that is this term, right, that is this term, okay, and this is this term. Is that okay? Now, so there are again very nice implications of this expression. Okay. So, therefore, Hamaker constant in the case where you have two dissimilar particles, that is 3 and 2, interacting via 1. Okay. So, you can write them in terms of the Hamaker constant for individual species when they are interacting in vacuum. Okay. So, one of the see you could, so if you look at this expression, you could have a case where either the first term could be negative and the second term is positive, or you could have a case. So, I could have a case where the first term is negative and the second term is positive, and the first term is positive, second term is negative, right, and both could be positive, both could be negative, the first and second term. Okay. Now, if you have this and this case, overall Hamaker constant is going to be positive, okay, in which case you can have a attractive interaction between the two particles 3 and 2 interacting via medium 1. But however, if you have case 1 and 2, you have A312 will become negative. That means, instead of Vanderwaal's attraction, you have what is called as a repulsive interaction that kick in because of Vanderwaals forces. Okay. So, one of the factor in the above equation can be positive and one can be negative, right, in which case the effective Hamaker constant itself becomes negative. Okay. That means, that is the pairwise attraction between the bodies, it actually results in a net repulsive forces if you have dissimilar particles. Okay. We mentioned that if you have same particles, that is 2 and 2 interacting via 1 or 3 and 3 interacting via 1, we said that the net Vanderwaals forces are always attractive, is what we mentioned. But however, if you have a case where I have two dissimilar particles interacting via medium 1, okay, it turns out that you can have a net repulsive force between the particles. Okay. And this will happen when each term in this particular expression, okay, would be of different sign, right. As I said, one could be positive, other one could be negative, okay, or the vice versa. Okay. And that would actually happen when this particular condition is met. A22 must be greater than A11, greater than A33, or A33 should be greater than A11, should be greater than A22. That means, if the value of A, okay, the value of A for the continuous phase, okay, is intermediate to the Hamaker constant for the two particles that you have considered, if that is the case, that is when this particular condition is met. Okay. So, if the Hamaker constant for the solvent molecules or the continuous phase or the liquid in which the particles are dispersed, if that is in between the Hamaker constant for the two particles that are dispersed, in such a case you could have A312 will be negative. That means, you will have a net repulsion between the particles. Okay. So, you can also think about extending this particular concept further, in which, because we have kind of developed we have discussed macroscopic theories that people have developed, in which you can relate Hamaker constant to the equilibrium separation distance between the molecules and gamma. Okay. So, you could actually, I can substitute for A, okay, for each of these Hamaker constants, and of course, if you assume that on an average if d naught, that is the equilibrium separation distance between the molecules, is very similar, okay, for both the particles and the dispersed phase and the continuous phase. If I take this d naught out, I can actually express A312 as 24 pi d naught square multiplied by gamma 3 half minus gamma 1 half multiplied by gamma 2 half minus gamma 1 half. Okay. So, you can also work out like this. I mean, this I think would be a nice approach if you are looking at something like, say, emulsion, for example. See, if you look at like, say, water droplets in decane, for example, okay, an oil, or if you are looking at decane droplets in water, okay, in such a case, when you are working with a liquid in liquid dispersion, okay, you can assume that your d naught, okay, it's very similar in magnitude. If that is the case, I can actually take d naught out, and then I can express gamma 312 in terms of the surface tension values itself. Okay. Okay, that again is of course an approximation. Okay, we are assuming that d naught values they are typically in a narrow range. If you look at d naught values for different liquids, you will see that again there was a table here. So, let me just go back to the table. Let us look at this table, right. This is d naught. Okay, these are compounds. Okay, there is heptane, dodecane, ecosane, SiO2, polystyrene, water. Okay, look at the numbers. They are if you except for water, right, 0.22, 0.18, 0.26, 0.22. Okay, they are all nanometers. It's a fairly narrow range, right. So, if you have cases like that, I could indeed go and look at approaches like this, where I can express Hamaker constant in terms of the surface tension itself, because value of d itself would be in a fairly narrow range. Okay. Okay, I just want to end with talking a little bit about Vanderwaal's attraction in nature. Okay, any examples that you have come across where you think that there exist cases where you can think about Vanderwaal forces or Vanderwaal's attraction in nature? The very famous example that everybody gives is geckos, right. Okay, so there is a lot of there have been a lot of recent experiments where people talk about how do these geckos stick to the walls, okay, and it turns out that it is because of Vanderwaal's forces. Okay, there are some really nice experiments that people have done. Okay, this is a result from a paper that appeared in Nature 2000. So, what they do is they say that this is the magnitude of adhesive force that they can produce, 10 Newton, that is really large. Okay, and and everything is kind of what they do is, this is a macroscopic picture of a gecko, right, and then you can look at the mesoscopic structure, when you look at its palm, for example. Then if you zoom in and if you look at it with a microscope, right, it turns out that they have what is called as setae, SETAE, okay, and each of this actually has a large number of tiny flat structures, okay, and that is the length scale here, that is 1 micron. Okay, and you can look, right, there are so many number that if you calculate the Vanderwaal's force of adhesion between each of these fiber like things and the wall, and if you add them up, because there are so many number, okay, so the number is something like that. Okay, there are about 5,000, okay, per nanometer square, sorry, per millimeter square, right, 5,000 per millimeter square, Okay. And if you assume that typical, if you look at a big gecko, you could have hundreds of millimeter square area. Okay. And if you sum up the van der Waals interaction because of each of them, okay, with the wall, it turns out that you really get a very huge number. Okay. So this is one example where you can think about. Of course, there are other examples as well. So I would like you guys to go back and read up a little bit about these aspects, looking at van der Waals attraction in things that you see in nature. Okay. So that would be the end of module 2. So so we have kind of looked at various aspects. So what I will do is we will try and think about some tutorial in the next class. So I have one problem, we can just quickly run through it. African green monkey kidney cells, okay, you can think about that as component 2, okay, were cultured, okay, on a suspension of collagen coated dextrin particles. So what you should think is you have a dextrin particle, okay, and that is coated collagen. Okay. And because collagen is biocompatible, because collagen is biocompatible, you can kind of you can make you can grow cells on it, right. You can think about something like, okay, this could be I will say kidney cells. Okay. So harvesting such cells is traditionally accomplished by scraping or ultrasonication or the use of chelating agents to disrupt cation bonding between surfaces 2 and 3. Okay. So that means if I have a dextrin particle which is coated with collagen, and if you culture such cells on the surface, it turns out that if you want to take the cells off now after you have cultured them, okay, I should somehow get them off from the surface, right. And people have practiced different kind of things, scraping, that is physical, using physical force, or using sonication, or you could add some agents, okay, which essentially some kind of a chelating agents, which, so if there is a kind of a bonding between these cells and the dextrin, okay, I add in a reagent and it helps you in disrupting that bond, and you can actually take kidney cells off from the surface. Okay. Now there's a study, okay, in which they reasoned that cells might be eluted, that means cells can be taken off from the surface by lowering the surface tension of the suspending medium 1. Okay. Whenever you do these things, you do it in a medium, right. That means I should imagine that I have a container with medium 1, okay, and I have dextrin which is coated with collagen, that is your component 3, okay, and on that you have kidney cells which is component 2. Okay. Now, okay, because people have reasoned out that cells might be eluted or easily removed from the surface of this particles of type 3 or the component 3 particles by lowering the surface tension of the suspending medium, that is of component 1. Okay. So the question is, what is the basis for this explanation? Why do you think that they are saying that I can reduce the surface tension of the medium and then elute the cells? So DMSO was incrementally added to cell carrier particle suspension. Okay. I have a fluid in which I have the components 2 which is attached onto particle 3, they are in a fluid medium 1. Okay, the fluid medium 1 is water, and to that they systematically add DMSO. Okay. So, this is an aqueous buffer solution is what they have, that is 1 is a aqueous buffer solution, and to that they are adding DMSO. Okay. And the surface tension of the eluting liquid, okay, the surface tension of the fluid that elutes the particle, okay, and the percentage yield of the harvested cells is given here. So, this is the volume percentage of DMSO that is added. So, which is of course increasing, 0 corresponds to case wherein you have only the buffer solution in water, and that is the surface tension, and this is a percentage yield. That means the amount of cells that have been extracted or eluted, okay, and it turns out that if you add about 90 percentage by volume of DMSO, your yield goes up to 80.1 percentage. Okay. Okay. For the solids, so for the solid, because this GAM 2 and 3 are solids, right, your 2 is a dextran coated with collagen, that is a solid particle, okay, that is number 3, right, that is a solid particle, and 2 is the kidney cells. Okay. So, they have estimated the surface tension values that is given. Okay. Now, the fact that with increasing the DMSO concentration the yield goes up, is this observation, okay, is this observation qualitatively consistent with the expectation? Is that what you expect? Okay, suggest some factors that might be reasonable for any quantitative discrepancy. Okay, that is the problem. Okay. Take a look at this problem, think about what could be happening. So, maybe we will try and discuss that in the next class.